A register is a bunch of flip-flops, the same clock, bunch of flip-flops. This is what flip-flops. The individual flip-flops are rectangles stacked on top of each other. Only the top one is labeled here, 1D. All shared signals, example, the clock input go to the notched common control block at the top of the stack. The logic block must add 1 onto the current value of the counter Q here. 1 value added. Current value of the counter Q to generate the next value of the counter. D suppose it has a propagation delay of 1 nanosecond. Propagation delay clock 1 high to QI 1 nanosecond. Clock 1 to DI, that is clock here. This first 1 nanosecond clock. Okay. Clock of high to DIE clock here 2 nanoseconds. Here 2 nanoseconds. Okay. All flip-flops change state with the near fraction of nanoseconds of each other. Okay. Clock. This clock signal 0, 1, 0, 1, 0, 1, 0. Q2, this one, delay. This is the delay, 1 nanosecond. Now, per Q, here 1 nanosecond. Okay. 1 nanosecond. Sorry, here 2 nanoseconds. Here 2 nanoseconds. Here 1 nanoseconds. Here 2 nanoseconds. 1 plus 1. Here also 1 plus 1. Here what you mentioned, DI, D2, Q2, QI. Okay. The ripple counter is positively slow. The delay between the active edge of the clock and the counter output given the correct values depend on the number of flip-flops in the circuit, and therefore the size of the counter is that is how many stages. A far better approach is to use the flip-flops together as a group and clock them using the same clock signal as shown here. The logic block is a combinatorial circuit which computes the next D value D2 0 to 2 colon from the current key value Q20. D has 3 bits D0, D1, D2. We use the notation D20 to represent this. The relationship between D and Q is simple. D2 is 0, equal to Q20 plus 1. Since the three output bits Q20 change within fraction of nanoseconds. Other nanosecond of each other, the circuit is one faster than the ripple counter. The delay is constant instead of dependent on the size of the counter. The circuit is known as synchronous sequential circuit because its function is synchronous to a signal clock. The function is the function is synchronous. The function is, for example, to a signal clock. Signal clock. If you record Q20 output value as a state value, it follows the finite number of states defined sequence. Okay, defined sequence. Therefore, it is also to a form of finite state machine. Finite state machine. Finite state machine. Note the notation with the arrows. Here. Notation with the arrows. Okay. Here we are going to introduction discuss about introduction to sequential design. Types of logic circuits. Logic circuits can be combination logic circuits. Outputs depends only the current inputs. Output depends only the outputs depends only the current inputs. Sequential logic circuits outputs depends not only current inputs but also past sequence of inputs. Combination logic circuits output depends only current inputs. Sequential logic circuits depends not only current inputs but also on the past sequence of inputs. Sequence means one next first next then next like this. So any event or any function. So in the circuits, outputs depend not only the current inputs, not only the current inputs. For example, this is the current input. Not only output, not only this depend, but also on the sequence of inputs, all the sequence inputs. But combination logic circuits, for example, this is combination logic circuits. Combination, full combination. So output depends upon input only here in combination. But sequence, many sequence is there, no? Fast sequence inputs depends upon, but not only current input. Sequential circuit model. Combination logic delay. Combinational logic delay. Sequential circuit models. In these circuit models, combinational logic delay. Combinational logic delay. These all are gate already knows. For this gate, function time 5 nanosecond. Here 5 nanosecond. This is timing delay. Here this gate 5 nanosecond. all get 5 nanosecond. Longest delay, this one, after this one, this one, here after this. Shortest delay, this part only. Longest delay, this part. Okay, this is A, B are the input. Longest time delay, 1, 2, 3, 4, 5 nanosecond. 5 times 1, 2, 3, 4. Sorry, 1, 2. So this is both, no? That's why 1, 2, 3, 4. 1, 2, 3, 4 for this, and then this one last 29 nanoseconds. Shortest time delay, that is this one. Longest time delay, this one, from here to here. We will use the longest delay to represent the combinational logic circuit delay. This delay only consider for longest delay to represent combinational logic delay. Combinational logic, we can say now CL, okay, short. Okay. Combination, so Glaude model. In this Glaude model, that same circuit, longest loss 29 already we have seen. So this is Glaude model. So here this is 20 nanosecond. So memory. Memory. We will add memory or registers to our logic circuits. Add register memory to our logic circuits. This will allow us to design sequential circuits. To add, we will add memory or register to our logic circuits. Okay. This will allow us to design sequential circuits. Okay. We will add memory registers we will represent registers with the following block diagram. We will represent registers with the following block diagram. Okay. Clock, reset, okay, clock and reset are control signals. Clock and reset are control signals. Yeah, NS and PS are data signals. This is and this is data signals. Okay. Okay, sequential systems, block diagrams. Okay. Sequential circuit systems